Alright, in this video I'll be talking about polynomial functions. And I do want to mention before we get started, this is a section where we're going to be doing a lot of factoring, so it's important that you maybe brush up on your factoring skills if you know that's a problem for you. But let's go ahead and get started. We're going to talk first about features of polynomial functions. In fact, a lot of what we're doing here is analyzing polynomial functions, and we're building a foundation for what we're going to do in the next section where we'll be graphing polynomial functions. So let's go ahead and get started. It says a polynomial function is of the form, and you've got p of x equals this long, challenging looking expression with all the subscripts. And really all it is, if you look at our four examples here, polynomial functions are real basic functions, some of which we've already studied, where you have terms with whole numbered exponents. Usually it's like x to the first, or x squared, or x cubed. So we have nice exponents with these. And so let's go ahead and get started by looking at A, where we have a linear function, f of x equals 1/3 x plus 1. And the thing that makes it linear is the x to the first power, so the degree here is 1. If you look at B, that's an example of a quadratic function which has a degree of 2. We say 4x squared here is our leading term, and that dictates or determines our degree here. And then and by the way, you can see I've included the graphs with these as well, because there's some things we want to look at with polynomial functions. So in C, we have a leading term. Notice the term with the highest degree has a degree of 4. So we call that the leading term, and its degree is 4. So the degree of the whole polynomial is 4. And then finally, if you look at the last one there, it's going to have a degree of 5 because of the x to the 5th power, which is our leading term. Now I just want to point something out, because this is something I'll refer to on the next slide. If you look at A and D, these both have odd degree. And I want to have you look at what's something that we refer to as the end behavior. Look on the left and the right on the ends of these two functions. And you can see that on one side the graph is falling, and on the other side the graph is rising. And so it turns out there's a nice pattern here. And now if you look at B and C, you can see these are both even degree. And if you look at the end behavior on these, something different is happening. The graph's either rising on both ends or falling on both ends. And so you might guess at what's going to be our generalization here. So let me get rid of all these marks. And let's go down here where it says a little bit more about polynomial functions. As the graphs demonstrate, polynomial functions, A, are continuous, meaning they have no breaks, holes, or gaps, and B, they have smooth rounded turns. Now if you look at the linear function, it doesn't have any turns, so we don't have to worry about that one. But on the other polynomial functions, all our turns are nice and smooth. So that's what we're saying here. And so let me give you a couple of examples of functions that are not polynomials. So for the first one here, you should recognize this is the graph of the absolute value function y equals absolute value x. And in fact, this has what we call a sharp corner. And so this is something that you won't see on polynomials. And then I would like you to look at the next one. We briefly have discussed this one, but it's y equals 1 over x. And this is a function we'll actually study in more detail in this chapter. But you can see at x equals 0, we have a break. There is no point on the graph at x equals 0. All right, so those are two examples of things that or functions that would not be polynomials. All right, let's move on to the next slide. So now we're going to generalize from some of the things we saw in the last slide. It says a polynomial in standard form has a degree equal to its greatest exponent. Consider the polynomials above, which we just did. The following can be observed from these graphs. Number one, even degree polynomials have graphs that either, and you want to say rise or fall on each end. We call this in behavior. Note the graphs B and C, or from graphs B and C, that sometimes these polynomials may cross the x-axis or not, and so that's something that is true for even degree polynomials. If you look at number 2 here, it says odd degree polynomials have graphs, and let's go ahead and put in rise and fall on opposite ends. Graphs that rise and fall on opposite ends. For this reason, the graphs of these polynomials are always going to cross the x-axis. So you can see graphs A and D above if you want to confirm that. All right, so let's practice now. It says for each polynomial function, determine the leading term, the leading coefficient, and the degree of the polynomial. Then classify the polynomial function as constant, linear, quadratic, cubic, or quartic. So for the first one here, the leading term is the term that has the biggest exponent, or the greatest exponent. So that's going to be the negative 3x squared. Our leading coefficient would be the number in front of the x squared there, which is negative 3. And so since our leading term has a degree of 2, the whole polynomial will have a degree of 2. And so this is a quadratic function. On number 2, let's see, our leading term is going to be the 0.2x cubed, which makes our leading coefficient 0.2 or 2/10. And so this is a third degree polynomial, or this polynomial has a degree of 3, and we call that a cubic function or polynomial. On number 3, well, I hope you recognize this is linear. Our leading term is 2x, the leading coefficient is 2, and so this is a first degree polynomial. That's what makes it linear. And then finally in number 4, just be careful here, the leading term is not necessarily first. In fact, the term with the biggest exponent comes last here. So our leading term is negative 3x to the 4th. Our leading coefficient is negative 3. And the degree of this polynomial is 4, which is the exponent on our leading term. And finally, this is a quartic function since its degree is 4. All right, let's move on to the next slide. And we're going to talk about in behavior in more detail. So you can see on number 5, I've graphed f of x equals x squared and x to the 4th. And for the most part, these graphs look quite the same, or very much the same. I want you to notice that the graph of x squared is actually this one here. And so x to the 4th, you'll notice I say it's kind of fat in the middle, or more, it's closer to the x-axis. It's kind of flatter looking in the middle there. And then you can see on the ends it's rising a lot faster than x squared because we're taking each input to the 4th power, so we're getting bigger numbers. This thing shoots up faster than x squared. But the bottom line is, what I really care about here is the in behavior. And you can see that it's rising on both ends, or rising on each end. On number 6, I've graphed f of x equals x cubed, which I call the John Travolta function. Let me see if you can hear this here. So if you haven't seen John Travolta in Saturday Night Fever, you got to see this dance. That's why I call it the John Travolta. Let me go ahead and get rid of that real quick. And then I want you to notice I've also graphed f of x equals x to the fifth. And again, it's kind of like before. It's very similar to the graph of x cubed. It's just kind of more flat looking in the middle. But the key is you can see on the end behavior, or as far as the end behavior is concerned, it's the same on both ends. Falls on the left, or the graph is falling on the left, and it's rising on the right. So if you look at number 7, you should be able to draw that graph. It's just a reflection through the x-axis. It actually has the opposite end behavior. Notice that it rises on the left and falls on the right. This is what I call a reverse John Travolta. So I'm trying to get that to stick in your head because I want you to know what the end behavior is for x cubed and minus x cubed here. And now on number 8 it says, what would the graph of f of x equals minus x to the fourth look like? And again, this is just a reflection through the x-axis of f of x equals x to the fourth. So when you graph this one, you should get a graph that looks something like that. Again, it's kind of flatter looking in the middle. And as far as end behavior is concerned, it falls on each end. Now, if you look at number 9 here, it says for each of the above graphs, the coefficient of x is 1. How is the end behavior of the graph affected if the coefficient is a number other than 1? So in this diagram, I graphed 0.2x squared, which is really 1/5 x squared, and I graphed f of x equals 10x squared. And you can see that the end behavior is unaffected by a coefficient other than 1 out front. And notice all these are positive. If they were negative, the graph would just open down instead of up. But the bottom line is the end behavior is unchanged. It really doesn't matter if we have a coefficient other than 1. So finally, I'm ready to generalize the whole point of this conversation. In number 10, it says the end behavior of the graph of a polynomial in standard form is determined by its leading term. All right, so let's talk about that in more detail. So our end behavior for a polynomial function is going to be determined by the leading term. All right, so let's move on to the next slide. And so this is sometimes called the leading coefficient or the leading term test. And so let's discuss it in more detail. So we're talking about the end behavior of polynomial functions. Now, first we're going to look at degree here. So if we have a polynomial function with odd degree, I would have you think of the function y equals x cubed, which I call the John Travolta function, which on the ends falls to the left and rises to the right. Now, you'll notice that we're going to look at two cases when our sign is, or the sign of the leading coefficient is positive, and also when it's negative. So if it's positive, it's going to have end behavior just like what we have here with y equals x cubed. It's going to fall on the left and rise on the right. Now, if you have a negative out front, we know that that reverses the end behavior, and so it's actually going to rise on the left and fall on the right. So what we're doing here is, this is a nice diagram that I would encourage you to use as a guide for you when you are testing or checking to see what the end behavior is. But eventually, I want this to get into your brain. I want you to be able to do this by, to know it and not have to refer to this diagram. All right, so when I think of, again, degree and even functions, I think of y equals x squared, which we know is a parabola that opens up. And so in behavior, it rises on both ends. So if we're looking at any power of x that's even, we're going to have the same kind of end behavior. If our leading coefficient is positive, then our graph's going to rise on both ends just like y equals x squared. If our if our leading coefficient is negative, then our graph's going to fall on both ends, and it'll look like this. All right, so keep this in mind as you do the following problems. All right, so on number 11, it says use the leading term test, or using the leading term test, match each of the following functions with one of the graphs below. All right. Well, let's see. On A, our leading term is the 3x to the 4th, and so we're even and we're positive. And so if you look at the chart, that makes, let's see, we're going to rise on both ends. And so that would be, whoops, let me go back. So that would be D. So A is D. All right, so I would encourage you to try the other three and then watch the video. All right, so on B, our leading term is negative 5x cubed, and so we're odd, our degree is odd, and because of that negative 5, our leading coefficient is negative, and so this is what I called the reverse John Travolta. And so let's see, that would be letter B. And so let's go ahead and put B here. So actually B is the graph B. All right, so let's look at C. Now for C, the leading term is x to the 5th. So here our degree is odd and we're positive. This is the John Travolta behavior. And so notice this is going to be graph A. And then finally, if you look at D, notice this is an even function and our leading coefficient is negative. And so this is going to be the case where it opens down on both ends. And so that's going to be graph C. All right, let's go ahead and move on to the next slide. Actually, I think I'll stop right here and we'll do a second video.